Okay, so following up on learning about the calculations that go with weak acids and bases and dealing with pH and concentration, we're going to look at the concept of salt hydrolysis, which is another way of saying the acid-base character of salts. So we know that whenever an acid reacts, we always produce an aqueous salt as one of the products. And although classic, table salt, something like NaCl, has a neutral character and doesn't affect pH in any way, there are many salts that actually can affect the pH of a solution. Um, and so this gets referred to as salt hydrolysis because it's referring to whether or not the salt has enough acid or base character to actually react with water and hydrolyze the water, which means split the water into H plus or OH minus ions. So it looks at whether or not the salt is acidic enough to donate protons to water, or is the salt basic enough to accept protons from water. The IB will refer to this as salt hydrolysis, but really think of it as does the salt have an acidic or a basic nature to it? So in order to explain this, I think an example helps. We're going to look at the quantitative relationships between a weak acid and its conjugate base. So we'll use the classic weak acid of ethanoic acid, and this is its dissociation equation with water. And here's its acid dissociation constant expression, the Ka value. If we look at its conjugate base, which is the ethanoate ion, if we look at that reacting with water on its own now, so here's ethanoate on the left, reacting with a water molecule. Well, it is a conjugate base, so if it acts as a base, it would accept a proton from water, which means it would produce a CH3COOH on the other side as the conjugate acid, and it would produce some OH minus. Now remember, this isn't happening much, but this is what would happen when it behaves like a base, and it's at equilibrium. So I can set up a similar Kb expression for the ethanoate ion when it acts as a base. It looks like this. So now what I'm going to do is if I take those two expressions, the Ka and the Kb, and I multiply them together, what you're going to see is that a lot of the terms in the two expressions are going to cancel. So the CH3COOH is going to cancel, and the ethanoate ions are going to cancel. And so actually all that's left over when you multiply the Ka and Kb together is H3O plus, which is like H plus, times OH minus. And this is the exact same as another expression that you've learned, which is the Kw. Kw equals H3O plus times OH minus. And Kw always equals 1 times 10 to the minus 14. So what happens is it turns out that if you take the Ka value of a weak acid and the Kb value for its conjugate base, when you multiply them together, they always have to multiply out to the same thing as the Kw of water, because when you multiply their two K expressions together, that's actually what they cancel out to. So I'll rewrite that down here. For any conjugate acid-base pair, when you multiply Ka and Kb together, it has to always equal out to 1 times 10 to the minus 14. And that also is going to mean that if you take the negative log base 10 of both sides and you get pKa's and pKb's, that they have to add up to 14, just like pH and pOH always had to add up to 14. So it's a very similar relationship that we had with H plus concentration and OH minus concentration always have to multiply together to this value. Well, Ka and Kb's always have to multiply together to this value if they are referring to a conjugate acid-base pair. And just like pH and pOH always add up to 14, pKa and pKb for a conjugate acid-base pair always have to add up to 14. So if you look at ethanoic acid, this is the pKa that's in the data booklet, and that corresponds to a Ka value of 1.74 times 10 to the minus 5. That means that the pKb of ethanoate, its conjugate base, is 9.24, and its Kb is 10 to the minus 9.24, which works out to 5.75 times 10 to the minus 10. And if you multiply these two values together, they should equal 10 to the minus 14. And if you add these two up, they add up to 14. So note that while ethanoate is a base. It is a conjugate base, and it does have some basic character to it. It's not a strong base. It's an extremely weak base. The lower a pK value is, the stronger that substance is, for whether it's acid or base character. So over here with a value of 4.76 compared to 9.24, ethanoic acid is a stronger acid than ethanoate is a base. And that makes sense because if you had a solution, it would contain both of these. We would still expect it to be an acidic solution from ethanoic acid being a weak acid. So the strength of an acid and its conjugate are related. But if you are referring to a substance that is a weak acid, its conjugate base will be an extremely weak base, but it will have some basic character to it. So to try to summarize what I was getting at there, if we think about the relationships, that as acids get stronger, what happens to their Ka values? Well, as acids get stronger, Ka values increase because there's more dissociation, and therefore the product part of the fraction goes up and the Ka value increases. But as Ka goes up, pKa decreases, pKa goes down. Just like as H plus goes up, pH goes down. So an important concept to remember for this topic is that the P values, whether it's pH, pOH, pKa, pKb, the lower they are, that implies stronger and higher concentration. Whereas the regular values like Ka, Kb, H plus, OH, the higher those values imply higher concentrations or higher strength. And so this is going to work the same way for the bases on the other side. But instead of Ka, pKa, it's Kb and pKb. So what do I mean by that? Well, as an acid gets stronger and stronger and stronger, it gets better and better at donating a proton. Its base will therefore be worse and worse and worse at accepting protons, right? If this thing up at the top, this is, or HCl like hydrochloric acid or perchloric acid here, they're very, very good at giving away protons, which implies that their conjugates are very, very bad at accepting protons. So the strongest acids have conjugate bases that are essentially neutral and have absolutely no acid-base character, whereas things like ethanoic acid that fall more in the middle of the spectrum are only weakly acidic, and therefore they have conjugates that have some strength as a base. Not much strength, but a little bit of basic character to it. And so just to drive that point home a little bit more, if you think about a Ka or pKa for something like hydrochloric acid, we don't even usually assign Ka values because we assume 100% dissociation. And so if something were to dissociate 100%, it would have a Ka value that was approximately equal to infinity. And therefore, it would have a pKa value. It would be basically zero. So that would imply that it was super duper strong. Its conjugate base, based on the relationship, therefore, this should say B, its Kb value would be almost zero, and its pKb value would be almost infinity. So it would be so weak that it would essentially have no basic character whatsoever, and it would be entirely neutral. So the overall relationship to come away with is that as an acid becomes stronger, its conjugate base will be weaker. So the weaker the acid, the stronger its conjugate base, and vice versa. As a base becomes stronger, the weaker its conjugate acid will be. So weak bases have conjugates that have some acidic character to them. And that's what we saw with this relationship here anyways. If the pKa here drops, then this pKb has to be higher. So the stronger the acid, the weaker the conjugate base, and vice versa. Okay, to bring this back to the idea of, okay, well, I'm going to pause this video and we will continue in a moment.